All right, folks, here we go. Video 2 for section 1010. All we're going to do is look at a few more examples of the alternating series error bound. Turn the page, we'll go to example 4 here. It says approximate an interval that contains the sum of the series, sum from 1 to infinity of negative 1 to the n plus 1 times 3 over n squared, using the alternating series error bound from an approximation using the first 6 terms. So first of all, we're coming up with an approximation, and then we're using the error bound as well. So first we need the approximation from the first 6 terms. And in order to get that, we need to, list out the first 6 terms. When n is 1, this is 3 over 1. When n is 2, this is, it's minus 3 over 4. Come on. Minus 3 over 4. When n is 3, it's plus 1/3, or 3/9. When n is 4, it's minus 3/16. When n is 5, it's plus 3/25. And when n is 6, it's minus 3/36, which I could have also written as 1/12. Now the error has to be less than the 7th term, which is going to be 3 over 49. Okay, now, how can I use this information to approximate an interval that has to contain the sum of the series? Well, we know that the error is 3 over 49, and we in fact know that it's in a positive direction since it's a positive term, which means that the actual value of the sum is going to be larger than the approximation that we get from these first 6 terms. So the first thing I'm going to do is I'm going to find the approximation from these first 6 terms. So 3 minus 3/4 plus 1/3 minus 3/16 plus 3/25 minus 3/36. And so we've got as our approximation here 2.4325. 2.4325. And my error term is 3 over 49. Which is approximately 0.0612. 0.0612. Should we call it 0.06122? Why not? All right, now that means our approximation has to be bigger than this, but it has to be smaller than the sum plus the error. So I'm going to take that error and I'm going to add to it the 2.4325, and that gives me 2.49372, etc., etc. When I'm writing an interval like this, we know that it has to be smaller than this, so we always round towards the center here. So I'm going to use 2.493.7. No, I'm not. I need to round out 2.4938 because it's possible that the sum could be above 2.4937 but below 2.4938. It's not likely, but just to be safe, I'm going to write this as 2.4938, round out, and I know that the sum of this series must be somewhere in between these two values. All right, example 5. Let f of x equals blah, 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 blah. Show that 1 minus 1 over 3 factorial approximates f of 1 with an error less than 0.01. Okay. So this is one of those really neat ones for us. Well, no, I shouldn't say that. So we're using the first 2 terms to approximate this. Therefore, the error is going to be less than the 3rd term, the next term here, at x equals 1. So the error is going to be less than 1 over 5 factorial. 1 over 5 factorial is 1 over 120, which is less than 0.01. Boom. I've shown that 1 minus 1 over 3 factorial approximates f of 1 with an error less than 0.01. All right. And example 6. For the alternating series blah, find an interval that the sum of the series must be in based off of the approximation from the first 7 terms and the corresponding alternating series error bound. This is almost identical to example number 4, except we are going to use a few more terms. So first I'm going to find the first 7 terms. So the first term is 1 over 2, and the second term is going to be minus 2 over 5, and then plus 3 over 10, then minus 4 over 17, plus 5 over 26, minus 6 over 37, plus 7 over 50. And the error term, the error has to be smaller than the next term, which is the absolute value of the error has to be less than the next term, which is 8 over 65, but this is going to be a negative value for us. The error is less than 8 over 65, but the approximation is going to be above the actual value of the summation. All right, so I want to sum up all these terms. Let me slide this a little bit so that I can see my calculator a little bit better. All right, so we've got 1/2 minus 2/5 plus 3/10 minus 4/17 plus 5/26 minus 6/37 plus 7/50, which gives us 0.33485. 0.33485 for our approximation, which we might just bump up to 0.33486 when we write the interval. And then the error is 8 over 65, or 0.12308, 0.12308. 12308. Okay, so as far as my interval goes, since this is a negative term, this is going to be the upper boundary of my interval. And so the sum has to be less than that, and it has to be more than this minus the error. And so I'm going to take this minus the error, and I get 0.21177. And so the actual value of this series must be somewhere in between 0.21177 and 0.33486. So that's how we can use the alternating series error bound to bound in the possibilities for the sum of a series and get us, at least in the right ballpark. All right, that brings us to the end of this video and the end of section 1010. Come back and join me for section 1011 next time. All right, until then, we'll see you. Have a great rest of your day.